Atmospheric pressure is real, guys. Check it out. All right, welcome back, guys, for another one of these induction series. And we've got a few more things to cover this week. Again, I want to thank everyone for all the questions. Thank Einstein Motors for bringing this and get into some of the comments, clear some things up. And just a quick one on the semantics, guys. I'm truly not interested in those types of comments. So if you're the sort of person who goes, no, it's not pressure, it's actually weight, just go, because it is weight. We've got basically 100 miles of air above us that creates that weight and pressure on our body, and we do feel it. What I should say is the weight on our body is real, and a lot of people say, oh, because it's inside, outside. All it has to do with is we were born on the planet with 14.7 pounds of atmospheric pressure. So every single thing down to your cell is already pressurized at that 14.7 pounds of atmospheric pressure. And we only notice it when we go down further or up higher. So we get in a plane or we go and climb a mountain, we'll see how our brain swells because we no longer have that weight, that pressure holding it together. So it is 100% a real thing. We just don't notice it because we've had thousands of years of evolution to get used to it. So we use a pressure differential with our diaphragm to help us breathe. And this works at minute levels of pressure differential. But yeah, call it what you like, guys. Keep the semantics for someone else. We're truly not interested. I want facts. And even I had some guy bringing in ChatGPT for an answer. Guys, please try and let's keep the level up here, not down here. I'm actually training AIs at the moment for Einstein Motors. They haven't got a clue yet. They're a very good tool. They're like a super smart, stupid person, as I like to say. They can get some things close, but they get a lot of the basics really, really wrong because a lot of the education process, they're just scraping off the net. And as anyone will know, if you've been on the internet long enough, you'll know 80% of the stuff that's out there is absolute junk. It's not factual. And especially when it comes to port design, there's a lot of aspects that don't cross over well, like with aerodynamics, and you're trying to explain surface finish and what's actually happening in a turbulent environment and an active boundary layer. So we're going to cover some of those things today. We're going to get into individual throttle bodies, bits and pieces, a little bit more on the boundary mechanism, why dimple ports aren't a great thing. And again, I've seen one of the comments from one of the guys in there, so thank you about Darren's comment. If you need dimples, they're only there for a problem you've created. So basically, in other words, learn how to port, right? They're a band-aid, so no. And the scale of a dimple compared to the scale of a burr is very, very different. They're day and night. So we really need to understand what's actually happening in there as far as boundary goes. And there's a couple of misnomers as far as aerodynamics versus ports. So in an aerodynamic type boundary mechanism, generally, as we increase velocity, we reduce our boundary layer. In a port, we tend to see the opposite, and that's to do with when a vehicle or an object cuts through space, air, it's cutting through 14.7 pounds of atmospheric pressure. But when a port and a piston creates a low pressure event and the atmosphere tries to fill the cylinder, the velocity in the port isn't at atmospheric pressure because now we have speed, we have velocity in the port. So we see a reduction in pressure, which means the boundary layer at atmospheric pressure can now expand, move. A high pressure will move to a low pressure, and the same things that happen at the macro are happening at the micro. So this is where there seems to be a little confusion, and this is why another reason why dimples won't work in a port, due to the magnitude of the boundary they create. Again, they choke it. And also wanted to clear up some things around what we're talking about as far as when we test it, when I've seen other people test it, is how it chokes the engine. So we see the power curve shift. The other problem we see with it, especially if we just take an optimized port and dimple it, what we see is a reduction in the power band. And that again comes down to our boundary layer being dynamic, meaning the thickness and how many molecules are colliding with our boundary or our surface and creating that thickness is also dynamic. So a lot of people say, oh, what happens if we just put dimples, along the floor, which is a brilliant idea. It sort of makes sense. It's logical because that's going to thicken and help the airspeed along the floor. The problem is the dimples aren't going to be active at lower engine speeds when we need the smaller cross-sectional area. Then as we increase RPM and now we have velocity, then the velocity, the boundary thickness is going to increase quickly, meaning we're choking our power window. Hopefully that makes sense. If not, put it in the comments and we'll expand on it. So, all right, let's get into the next part. All right, guys, another quick thing I'd clear up, and this might help a few people out there. I had a comment, oh, let's not get this guy to size my carby. I actually find those comments hilarious because if you've read a book or picked up Street Machine, some of the carby sizes that we would recommend, you might actually freak out. And that's to do with, again, pressure differential. Everything is pressure differential. You'll hear me talk about it all the time. That's because we need to understand what we're actually creating. Doesn't matter if it's on the exhaust side or the intake side. It's all about harnessing that pressure and making it work for you. And not only at an average, at a sinusoidal wave as well, using those waves to help tune the engine and obviously reduce how much horsepower you need to give away. So again, pressure differential. So I wanted to talk about carb size because I was of the same belief before getting into testing years ago. And when we first started building some of our first tunnel rams, and this is why you'll see tunnel rams like dual planes tend to like far more carburation than a single plane. And that's to do with these pressure differentials and the wave cycle that is created inside the plenum. So I'll just break it down really quickly. And I actually had a video sent to me by from someone, and it was one of Eric Weiner's video, or Weiner, sorry if I wrecked the name, but really, really good and really good to see. He's learnt the same sort of lessons that I have testing tunnel rams. And again, sort of from the early 2000s and on, we were building a ton of tunnel rams and doing a ton of testing. It was in those first early years that, I used the Holy calculator and, again, all based on, 0.85 VEs. And it come up that this 350 Chev needed 2465 carburetors. So sure enough, that's what we did and put that on and found out really, really quickly that it wasn't even close to what we needed. And we ended up with basically two 650s. And then we actually dynoed it with two race 725s, and it was absolutely unbelievable. We made another 25 horsepower, and the engine was great from even 3,000 RPM. The car had a 4200 converter in it, so it was really, really good. But I'll put Eric's video in there because he actually took, I think it was a 406 cube, nothing crazy. I think it was 68 or 7,000 RPM. So realistically, the Holy calculator would tell us that needs maybe 850 to 1,000 CFM. And anyway, he tested basically 1,000 CFM single plane and then went to dual 1,000 on a tunnel ram. And again, and seen great results, pulled it nice and early, seen no problems. And as he explained, if you can load something like that on the dyno low, like 34, 3500, you'll have no problem on the street, especially once you've got a converter. Because a good converter, and in the early days when we were doing a lot of 11-second combos and Holden engines and stuff like that, straight away we put 5200 converters in them and people would absolutely freak out. And actually I had one customer, and you always, every now and again, you get that customer that you're just constantly butting heads with and he's second guessing your work. And this was a proven combo. We'd done maybe 25 of these. So we knew the pipe, we knew the head, and they were really, really basic combos. So back then there's the SRP hyperneutectic flat top, 1025 to 1, real simple. Would run them, would run a VN head that would pocket port. If it was a again, pump fuel would, 248, 252, 256, depending on what the car was, on 108 or 110, depending on where they wanted the power. Set a pacemaker exhaust, twin 3-inch X pipe, and 52, 5500 converter. And people would absolutely freak out. And we used to get Dominator converters to build the converters for these. And like anything, a really good converter, they're like, oh, I don't want to take off at $5,000. It's not how a converter works. You need to make 450 foot-pounds to shear that at 55, 50, 200 RPM. So you could get in these things and put it in gear and it'll go clunk, and you could take off and cruise along the freeway at, 2.5, 2200 RPM, no problem, until you went to the floor. And this is the other important thing, especially once you get into serious engines like serious comp, like drag engines are generally over-comped compared to an endurance engine because they're short sustained. So you can get away with more comp because you're leaching heat into the engine. You've got a lower thermal efficiency rate. Now, this is why you got to be careful with compression ratios and thermal barriers and stuff like that. So, but basically what we had was he didn't put the right converter in. He wanted an 11-second car. He had 3 other engines built with another engine builder, and originally we quoted it, I think we were like $500 dearer. So we went with the other dude. And anyway, he ended up coming back 2 years later and telling us about all the problems he'd had. I said, look, Joe, no dramas, we can sort it out. This is what we've got to do. And from the start, the gearbox guy argued, because again, a higher stall obviously runs a little bit hotter, so you need transcooler, and some of the guys don't like it. He was with a transmission guy that I didn't use, so I just said to him, look, this is what we need, do it. Anyway, the car come back with a 3.5 stall, and this will just show you how little parts of the equation, if not done right, can have major effects on the car. So not only did it not have the right size converter, the pipes, they pretty much stepped down really quickly and ran 2.5s each side, no crossover. The car, to me, felt absolutely horrible, lazy. Again, we're loading the engine before torque, and that was the point I was trying to make before. And it didn't really matter in this combo. It's just, this is what we'd established what works. But if you've got a serious, 12.5, 13-to-1 pump fuel engine with a big camshaft, you don't want to load that before its peak torque point. And this is the idea of a big converter, is when we tromp it, it will go past that critical area where the engine isn't harmonically sound. Things aren't happening well. So that's what a converter tends to do. It's like dumping the clutch at $5,000 in a way. So anyway, the car basically went 1250s, and he comes in, he goes, oh, I'm not happy. I said, well, are we about to start listening? I said 5200 minimal. I said 3-inch exhaust, crossover, do it right. Anyway, long story short, sure enough, he comes back in almost crying, hugs me, and goes, yes, I did it. I've finally got an 11-second car, because again, you got the right converter, got the right pipes, and now the combo worked. Again, we played with this with different carby size. I think we ended up with an 850 on this one with a Harrop manifold, and you could do the combo far better today with the parts that are out there. But my point was, you really have to understand how every system affects every part of that engine. The exhaust affects the induction. I've had guys on the dynos, like actually it was a Melbourne build I sent down, and the guys are on the dyno, similar thing, and they're like, dude, this engine hates this carby. They put a 650 on it and it ran better. And I'm like, no, something isn't right. So sure enough, what have you done here? Anyway, they put these absolute junk Chinese mufflers on the engine. They're absolutely choking the crap out of it. So they end up taking the muffler off, and straight away it performed better with the 850. And then they actually put a megaphone muffler, one of the brands that really good flowing muffler on it, and sure enough the combo works. So you really got to be careful what you do to different areas of the engine, because they'll have a synergistic effect across the whole combination. And carby is one of those things. So I just want to get into wave cycling and how we can harness each pressure wave. And this is the same and feeds into turbochargers when we start getting into equal length runners, and also split pulse turbo housings, and the point of harnessing the dynamic pressure wave, not just the average pressure. So when we measure back pressure on turbo cars, we just measure the average. But once you start getting into those dynamic waves, you can use that extra force of that dynamic by using greater pressure differentials, and carburation is exactly the same, but in the negative. So instead of using a positive, we're using a negative velocity wave that's going to hit the carburetor. So I've just drawn, this is a basic tunnel ram, and why tunnel rams will like far more carburation. So generally, as a rule of thumb, I tell a lot of guys, if you've got a combination that works really well, you can pretty much times that by 80%. And as Eric's shown, he did it, times it by 100%. Times your CFM by 80%, and that's a really, really good starting point. That you don't have to calculate VEs, you don't have to calculate anything. If I've got a small block Chevy, 400 cube, and it's got a 950 on it, and I've tested a few carbs and it's happy with that, and I go to a well-designed tunnel ram, and again, well-designed tunnel ram, it'll want 80% more CFM, and your jetting will be very, very similar, maybe even 90%. And again, as Eric showed here, so I'll put that video in the description so you guys can go and watch it. And if you don't follow him, follow him. He's a really, really intelligent guy, does some really, really great stuff. But why we see this difference is because we can harness each of those pressure waves, and on the negative side though. So every time the velocity starts, the valve opens, and this is why I say when you're designing carburetors, manifolds especially, my butterfly, I always like to see 80% of that runner under it. And this is exactly why, because we want to harness that negative pressure wave coming out that's going to hit the booster. It's going to spike the booster. It's going to improve atomization, meaning we're going to get smaller DSM, smaller particles of fuel, because we're harnessing this negative wave. So as that negative wave shoots out and hits the booster, it spikes the pressure differential between atmospheric and this low that this cylinder is creating. And this is why we want 8 butterflies for 8 runners. And this is what allows us a more dynamic signal to each booster of that carburetor. And this is why in serious NA cars, you'll see them go to split carburation. So I've got a build that's coming up from Melbourne really, really soon. Again, half serious NA that will run split carby, so we might even do a little video on that. But the difference by moving them out, not only can you go bigger in carburetor size, you can really harness that pressure wave, that negative pressure wave. So when I'm saying pressure, it could be either way. Please don't save the semantics, guys. So harnessing the actual dynamic element of that wave through the booster will improve how much horsepower it can make, and again, also improve the DSM, the fuel droplet size, everything, because we're not getting a dulled out average, right? So even NASA's got into this with their space travel using pulse-generated engines, right? So they pulse instead of continuous thrust, right? Because they can use that positive energy. So greater pressure differential, that's what it's all about. So in a tunnel ram, you'll see these negative waves will go up and increase the booster signal, help the atomization, pull it apart, and it does it per cylinder. Obviously, we're going to get some spread in here, but in a single plane manifold, and I'll get into this is why dual planes will like the same, will like more carburation than a single plane. And again, it comes down to that 180-degree separation. So on a small block Chevy, you've heard it talk about it before, 5 and 7 being very close in the firing order. If we look at this, so we've got 5 followed by 7, very, very close. So in a single plane, this obviously causes a problem. So when they designed dual plane, obviously the design isn't great as far as bends and stuff like that, but as far as wave harmonics. They're a really, really good design. And this is why, because they're based on 180-degree separation. So in a single plane, this is what we're going to get. Say 1, 8, da, 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 da. So this will give us an average negative pressure gradient, but our pressure differential is only from here to here because we have overlapping waves. So our PD is much shorter. But in a 180-degree plenum, and much like the inverse of that in a split pulse turbo, if we can separate the pressure waves in two planes, now we're harnessing every single pressure wave or negative pressure pulse. And now our PD is far greater, almost double. And this is why, again, carbies are all about signal. So if we can improve the signal by improving the pressure differential, we're able to run a bigger carbie. Because again, remember, a carbie gives away horsepower. The smaller the carbie is, the more pressure we lose across it. So it's got to sacrifice pressure drop to lift the fuel. And the other thing that comes into this is race carbies as well. The better the carbie is, the less pressure differential it needs to sacrifice between atmospheric and manifold, right? That's another aspect to look at. So again, there's guys spending big dollars on carbies, you know. Even your entry-level race carbies like APD, I've seen those things make 25 horsepower on a, you know, 500 horsepower small block for nothing. Same carbie. Pull a 750 Holly off and put one of these on and go 18, 19, 22, 25 horsepower. Again, they don't have to give away as much pressure drop to lift that fuel and atomize it. It's all a balance. But yeah, this is why you'll see a tunnel ram wanting far more carburation than a single plane, and also why a dual plane, you know, you see it with the old Rochesters, you know, 351, all that sort of stuff, big carbies, the Commodores, again, they're on 180-degree split. And this is the other reason why firing order is so important with a dual plane manifold. You've got to make sure it's right. I've had guys swap Chevy firing orders just for the sake of it because they could buy a cheap camshaft, use a dual plane, and then wonder why it wasn't great, wonder why cylinders are down. Again, these are based on 180-degree separation. As you can see here, 5 and 7 are no longer on the same path. And that's another area too. You got to be really careful not to cut that down too much and turn it back into a common plenum, right? Because they'll start interchanging. But all right, on to the next part. All right, guys, we're going to get into individual throttle bodies. But first, I just wanted to post this up. That's a bowling ball I was talking about that I think it was Navarre, the military division, testing basically how to trip that boundary layer, create those surface turbulence, so an active turbulent boundary layer. And all they basically did was take a smooth bowling ball and sanded it. I think it was like with 320 grit. So as you can see, really small amounts of texture will make an active boundary layer and help it conform to that. I think that was dropped at 25 feet per second, something like that. It's out of one of the fluid mechanics studies that we're going to pop up on Einstein Motors for all the gold members there. We're trying to build, or I'm trying to organize a library of basically fluid dynamic studies and fluid physics in general, so guys can read. I'm going to put some OEM studies that I've got, because I've probably got a few hundred. Some are good, some are absolute junk. So I'm basically going to be doing just simple reviews so people can do a quick read review on it, see if it's worthwhile. But there's some absolute gold in these studies. Some are really long. This fluid mechanics one's probably 500 pages long, so it really is a course into fluid mechanics. If that interests you guys, you can get on there and read it. But just with the surfacing, be really careful not just to focus on skin drag, because there's a lot of other factors, especially just with RA. Last week we talked about different profiles of the same RA creating two different skin drags. So again, if we've got something that's pointy, it's obviously going to have more drag than something that's rounded of the same RA. And this is where you get into RA profiling for different skin friction, different drags. But we also got to look at the thermal elements of that. And I was talking to a guy in Europe that experiments with cylinder head flow, and I think he's done some work with F1, but he's actually flow testing cylinder heads now at 90 and 100 degrees to see that effect of that boundary condition, because that's another aspect we need to look at. Again, we know that a high pressure feels a low pressure if the boundary layer is slow. Another way to speed that up and reduce the differential is to have a thermal element in it, meaning, and we do this with our plenums, and again, it seems to work on our street strip stuff. I haven't tested it on big NA stuff, but basically a texture finish on the port will create more convection, and we know this. So generally the coarser we get, the more exchange we get, because the more surface area is available to exchange that heat. This is why we want polished exhaust ports, not polished intakes. And that convection tends to create a almost like a vapor layer of warm air along the surface, which actually makes the drag coefficient drop as well. But it's about the balance. So we've really got to get that balance between texture and burr and finishes and stuff like that. And I think this is why we've found, and even Princeton University, Formula One, everything, between that 100 and 200 RA seems to be the sweet spot of everything combined. And this is where CFD really fails, because there's so much happening that it can't model everything. Again, most of the RAN systems fall short because they just don't have the computer power, and there's a lot of estimations in their process. So yes, they'll get you 95, 97% there, but that last 2 or 3% really needs real world testing. I had another question also about dimpled carby plates. Again, I wouldn't have a clue how they're going to work on carby. The idea is there. It's something that we're going to have to see in testing. I think Darren Morgan was talking about this the other day, and I've seen Eric testing some that was sent to him. But where I have seen it work is on piston crowns in the early days. If you've got a particular area that is getting wet down a poor chamber, dimpling that, or dimpling the crown of the piston. I think GM even released a performance engine with this in it in the 90s. I'd have to find that. But again, a thicker boundary on top of a piston isn't going to choke our engine in any way. It's only going to protect the surface of the piston, try and keep fuel off it. So as far as thinking about that logically, it tends to work. And I think that's what GM showed, better fuel economy and so on, because the less fuel we're putting on pistons and chambers, the more we're going to burn it, the more efficient it becomes, the more power we make, the less fuel we need, right? So in those aspects, yes, I had some comments about dimpling in other areas, plenums, low-speed piping and stuff like that. There's definitely something to be had using them in there. As far as a carby spacer, I'm not sure. Haven't seen the data for or against as yet. A little bit more shear time around that might be a good thing. Again, I don't really know. It's something that people would have to test. And again, with carby spacers, it really comes down to combination specific. Again, it's how well the whole system is working, what you need to compensate for. And again, with single planes, obviously very different to tunnel rams, because again, tunnel rams will have that dead area for negative wave suppression or positive wave suppression, where single planes don't. So they might need some sort of anti-reversion suppression in order. So that's why, a nice tapered, 4-inch or 2-inch super sucker design or something may or may not work. So real world. And then there's another aspect there that I've found as well, is depending on carburetor height due to the secondary wave. So you might go and put a spacer in and it didn't work, then you go and put another 1/2 inch or inch in, and then it does work. It's just where it was in the harmonics of the engine as well. So we need to look into that. So I'm just going to go through IR quickly, individual throttle body. Again, I haven't done huge testing in this area, but I've done a little bit. I've helped some guys here and there with it, and there is some tricks and there is some confusion. As far as harmonic length goes, pretty much the same third harmonic calculations you'll use for any manifold will work, because we're using the sound of speed, and as speed doesn't really change unless we're talking temperature wise, then you can pretty much use that calculation. But I'll explain where I see a lot of people going wrong as far as runner lengths with parallel tubes, and that fight between velocity and harmonic. And that's our first example, is a straight runnered or straight belled throttle body. And also the transition tends to be huge when people are doing this. So if we look at averages, depending on where they're targeting their average CSA, again, airspeed is going to affect our open wave, because again, speed is the speed of sound is relative to velocity, and that's another aspect I really should go into, and why we use averages rather than trying to calculate the wave. We're going to use averages, and why targeting the right average cross-sectional area also affects the runner length. So, and by that I mean the airspeed here is the same as the airspeed there. So if this was, say, harmonically perfect, we did the math and it said 11 inch, and we go and put 11 inch in there, you'll find that will hurt top end, that'll hurt horsepower. You might find it's going to work better at 9.5 or 10. That's because we're now getting a velocity restriction, and we can't get to our harmonic length to use it. Where if it was tapered, say something like this, then we could use it. Ignoring the throttle position, I'm just trying to show you how that as we move the throttle body up, we reduce the airspeed across the throttle body. Because if you, a lot of guys online, I actually put some figures down there that people will claim horsepower of throttle body. So 40 mil, roughly 60 horsepower. So if we've got four sixes, pretty easy for you. So 42, 70, and so on. The problem I have with this is it's not airspeed indexed, and this will highlight that. So let's say this one here is at 240 feet per second, but this one's at 200. And that's generally, I don't like to go under that. That's why I prefer a throttle body further away from the engine. Last week we were talking about, obviously, the eddy trail that they will create is up to 6 to 8 inches long before that will settle, major eddies. So that eats cross-sectional area. So if we were to CFD a throttle plate, you'll see a lot of high-speed area. When the throttle is even in the straight position, we end up with a wake after it, and we'll get these little eddies. So as we move the throttle away, we're obviously not seeing as much separation around the throttle plate. That's why I like them sub 200 or 200 and under. Again, if your entry's around 180, that means we're trying to get it nice and close to the top. This will give us also less morphing. You'll see a lot of them, especially when we're doing the Holdens and stuff like that. That's the port, and that's the 45 or 48 mil butterfly over the top. So the air really needs to morph to a different shape in a really, really short area, which is also a hindrance to make good horsepower. Again, good port design is about being as gentle as possible and creating as least amount of restriction as well. This will create axial morphing, meaning the air that's here has to get pushed in and then into that shape, right? So in a very, very short period. That's why I don't like them at the port. I like them out here, because if those two shapes were only, say, 2 inches apart versus 6 inches apart, which one's going to do better? Obviously, the one with the less angles and the less morphing over a longer distance. It's changing the shape far more gentle over a long time period, and hence you'll see the results in horsepower. So average cross-sectional area versus this average cross-sectional area. In something like this, we can actually get less cross-sectional area as well, depending on the diameter of the butterfly. So while these are a great, generalization, they don't come with an airspeed index. So you can actually put, with systems like this, go to a bigger butterfly for less horsepower and still have it work well. That's another aspect too. And also, tapered throttle bodies tend to make more horsepower. So FI Hardware, there's a few companies out there that make an actual tapered throttle body, meaning the top is bigger than the bottom. So rather than the throttle body being parallel, the actual throttle body has a taper in it, 3 degree or whatever they've based it on, which tends to make the transition a lot better. And then you can actually get down to the throttle blade shape. And I'll just pop up on the screen here. You'll see, and that's a CFD of 2 different types of butterflies and how each one creates different restriction. I built a calculator years ago for throttle body size based on airspeed, and I've got one up on Einstein Motors that I designed, and you can actually take into account the shaft diameter, because a lot of good manufacturers will actually mill flats on this, which actually reduces how much surface area that throttle is taking up in that cross-sectional area. Because here's the problem with this, say a 40 mil is worth 60 horsepower on what throttle shaft diameter? 10 mil that's been milled down to 8 or 6 or what size throttle plate? Some are at 1.6, some are at 2 mil and so on. This is why you'll see the same throttle body size with different CFM ratings. And the other thing to be careful of CFM ratings on a throttle body is that airspeed's far too high. So we get a 90 mil, fast throttle body and it's 1100 CFM. The problem is that 1100 CFM is at 28 inches. So your average velocity is going to be 350 feet per second through that throttle body. I don't like them anywhere near that. So again, my targets are like 200, 150 if you're trying to make big power. So yeah, it really depends where it is. But as far as induction length goes, if you're targeting the third harmonic, obviously we're going to be roughly the same length. And obviously the third is best. But you've got to watch stuff like this. If we've got a smaller throttle body and a very parallel straight tube, it's naturally going to want to be shorter. This is what I like personally. Get it nice and long. Use the tapered runner because again, parallel tubes distant over time creates more restriction. We don't want the velocity the same here as it is there because it's time over restriction. We're creating restriction. We want to reduce restriction, hence why we use a taper, because it's going to be less restriction because there's less speed and also less temperature. By that I mean the air that's traveled through there, due to its speed, if it's 240 feet per second, we have far more interaction in the boundary layer, which means we're getting more convection and more temperature loss. So now the air isn't as dense as it would be in something like this. So there's little things, and again, guys, these are all 1 or 2% stuff. They're not major horsepower, but everything, motorsport's all about collecting 1s, 2s, 3s, 4s from wherever you can and having that synergy from start to finish, from the air cleaner to the tailpipe, right? So again, these are real rough estimates if you're using your normal throttle plate type stuff. And again, I wanted to talk about obviously morphing. So hopefully you understand what I mean by changing shapes really quickly costs you horsepower. Again, it's only in the percentiles, 1, 2, 3, not a lot, but this is all things you need to look at. And the other thing we had interesting, and I was actually talking to a guy about it the other day, which we seen probably a decade ago. It was having a parallel system that was with a butterfly that was too big. And we end up making these little inserts so we could speed air up here. And what it actually does is trick the engine and increase our average cross-sectional area. And the engine actually worked. It actually made more horsepower. But that was just compensating for a poorly sized throttle plate. I think it was too big in the wrong area. We had a lot of morphing after it because it was very close to the cylinder head, like the early endly, stuff like that. They're really, really close to the cylinder head. So we did something like this and we actually seen horsepower. So we were able to trick the engine by tightening the CSA at the top, just making little inserts, and it worked on our averages. So now our average velocity is higher. We picked it up, created a little bit more ram air, and we're able to fill the engine after bottom dead center. Again, this is where intake valve timing, and we might get into camshafts as well later on. Intake valve timing is linked to your runner length. So shorter runner lengths will never be able to have as much after BDC timing as a harmonically optimized runner length due to this inertia mechanism. So again, I'll probably have to get into that in another video, but the closer and the better we optimize the length and the velocity, the inertia, the longer we can keep filling that cylinder as the piston comes back up from BDC. And the runner length is directly correlated to that, right? So as we shorten the runner, we don't have as much inertia, so we'll get more spill back. And this is where you see a shift in the torque curve, right? Because remember, peak torque is where the air is stalling and we're shutting the valve, right? Because we have an early and late velocity curve in the intake. So as we increase RPM, I might actually clean the board off. I'll clean the board off and I'll get into this just quickly. We'll cover it and then maybe do even more. Talk about the blowdown phase and stuff like that with exhaust timing and intake timing. All right, let's do it. All right, so real quickly, I'll just talk about this inlet pressure wave and the runner length and how it arrives at our peak torque point, which is what will happen. So basically, inlet opening, inlet closing. I'm not going to mention BDC or anything at the moment, but if we look at the black curve, that's our peak torque point. So, and this is why we'll see maximum VEs at our peak torque point. It's the quietest part of our engine as well. And that's because we're closing the valve, and this is a velocity curve, so 0, peak velocity, and comes back. So it's slowing, 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 and then we shut the exhaust valve. And that'll happen at peak torque. What happens before peak torque is our spill back. So as you can see, this is going into a negative. So this is earlier in the RPM. It'll come down, come down, come down. And now we've switched into a negative. So now we're pumping air back up into the intake pre-torque. That's this section here. So it's going back up into the intake. And then as we increase our RPM past peak torque, now we end up with a positive velocity wave ending up at the valve. And again, we use that as well as a harmonic event. But as you can see, this gets later in the RPM curve, but at peak torque, it'll actually finish, and that's where you'll see it on the dyno. No matter what you do with the camshaft, it generally always finishes at this point, unless you've really got everything wrong. But what affects this curve is the runner length. So this is why you've got to get the runner phased with the camshaft as well. So get the runner right and then test the intake to see where the wave is. And you'll see that with your torque curve, whether you want it more or less. And our intake valve closing events will affect this point, whether we're getting spillback. And you'll see some engines, we've had cylinder heads come in and the whole port is carbonated up the short turn and absolutely horrible. And then that's an indication of too much, too late a closing event on the intake. Really, really common. But yeah, this pressure wave, this also gets blamed for like valve seats and stuff like that. When people get runner length really, really long, we see this in a lot of OEM stuff. You put the right manifold on and now the engine doesn't have valve float anymore because the runner length was right. And you're not creating this pressure wave hitting the valve seat. And this is where a lot of people get confused with boost on valve diameters and stuff like that. It's like, oh, I've got a 2-inch valve, times that by the area and I need X amount more spring pressure. It doesn't really work like that. If your runner length is tuned right, and generally this is why you find a lot of guys will be on the shorter side on turbo cars, because they don't have to worry about this wave. Because if it's just density shift as boost, the pressure differential is equal. So this is a velocity mechanism, not a density mechanism. So this is where some people get confused. Anyway, that'll do it for this week, guys. I'll see you next time.